Problem number 1, you're adding the 3 elements of the pitching moment that I gave you on the assignment. So that's really all you do. It's just add those 3 pitching moments together. So since it's so easy, you need to show me that you're doing the work. So show the step. Where you're adding, just list all 3 terms together with plus signs in between, and you're good. Make sure that you put it, then you show me the step where you're putting it into the form of the stuff that does not multiply alpha wing body and the stuff that does. So you're separating out the stuff after you add it together. Make sure you show me that. And then show the definitions. This is CM0 bar because we're still in terms of LT, not LT bar. And we're in terms of alpha wing body. And then make sure you show me that you identified that as CM alpha. Easy, right? Just make sure you do those 3 steps. Huh? But everything should match what we did in the previous homework here. And the difference between in class and the canard is that for the horizontal tail, it's downwash, so we have minus signs for that. And for the canard, we consider it upwash. So there's plus signs for that. So that might be what you're talking about. Yeah, so there's like 1 minus d epsilon d alpha for the horizontal tail, and for this, there's 1 plus d epsilon d alpha. And it's plus epsilon 0 rather than minus. It's because for the angle of attack of the horizontal tail, it's alpha wing body minus IT minus epsilon 0 minus d epsilon d alpha times alpha. And for the canard, we identify IT IC as positive up, and then we say it's upwash rather than downwash. So that, I think that should account for the differences in the signs. Make sense? All right, other questions? Anybody in the chat? Do March 26th. What does it say on the assignment? Do I have the actual page? The assignment says due on February 24th and upload to Blackboard by February 26th. So you guys on chat, where are you seeing March 20th? No, part 2 is due next Friday.
Yeah, I think Blackboard thinks it's this Friday.
Well, Blackboard is always in control, right? So did I botch that up? Oh, hang on. I think it's on the actual assignment. I'm looking at, because I have it here, I have March 26th, and that's not due on March 26th, it's due on March 5th. So I'll double check that. This is part 2 we're talking about. I'll check Blackboard and I'll update this because there's a typo here. All right, thanks for pointing that out. Okay, what's next? So problem number 2. So you're calculating the wing, or sorry, the canard area and the aspect ratio. So that's just the standard formula. Aspect ratio is b squared over s. The area is the average of the trip, tip, and root chord. So the numbers you should be getting for these are those. Are we matching, you guys here? So I just gave you the answer. So what am I going to grade? I'm going to grade your work. So show the formula, and then with numbers substituted. Otherwise, all I know is that you copied this number down in your notes and you wrote it on your homework. You didn't actually do it. And why do I care whether you do it or not? It's more than just whether you get a grade or not. It's that when you come out of this class, you're supposed to know how to do this stuff. And so that's you're demonstrating that you know how to do it. Let's see some other intermediate answers that you're going to need to calculate the lift curve slope. We use the half chord formula that we've had for a while. You guys have done this before. You should be getting that number. And then for big K, this is the aspect ratio less than 4, right? Because our aspect ratio is 3. Is it less than 4 or 5? I've forgotten. 4? It's the split between the two. So you should get big K of that. We're matching? Good. And then I told you little k, well, I told you that the lift curve slope of the canard we just assume is 2 pi, so we get 1 for this. And we're still Mach 0, so beta should be 1, which all plugs into the canard lift curve slope big formula. You should get that. Again, show me your calculations, show me the work. So I'm giving you these answers so you get feedback and you can go fix it up, right? Let's see, the next thing we need to calculate LC and LC bar. And so this is the distance from the CG to the canard. And this is the distance from the aerodynamic center of the wing to the canard aerodynamic center of the wing. So I'm going to put the picture up there, and I've drawn these distances on there. So there's the figure, and there's the two distances. So LC is the distance from the AC of the canard to the CG. And notice how we've defined it here as positive forward. With the tail, we had defined it as positive aft. And then LC bar is this distance here. So really, this is just adding and subtracting numbers. LC is 10 plus 8. So that's that total deal, minus 2.75 minus this distance here. So it's just geometry. Yeah.
For part B, is that kind of just a statement rather than the assumption?
Where I say the wing lift curve slope was calculated in homework number 1 as that value. Yeah, it sounds like a statement, doesn't it? Yeah, that's all it is. I'm just giving you that number. And then LC bar is this distance, so you take 8 plus 10 plus 5.2 minus 2.565, and you get the distance there. So you should be getting distances for this. And then it asks you to calculate H and HN wing body. And you're given X, the distance to the CG is 2.75 on the figure. It's forward, so it's negative. And that's said in the homework. We define that as negative forward for that based on the way we've defined H before. It's always after the CG is positive. And then HN wing body is the same thing. It's the distance back to the aerodynamic center from the datum. So if you notice, these numbers come from these X bar, the locations of the aerodynamic center, X bar of the canard and X bar, that we calculate using those formulas in the appendix in the book. So that's why we learned how to calculate the aerodynamic center location, and that's where we get these values H and wing body now. So answers for these. And then the last thing is VC. Should come out to be 0.4803, and you're just plugging in the other numbers like the wing area and the chord length and the L's that you calculated there. So again, I've given you all the answers, so make sure you show me the formula that you used to calculate this, that you actually did the work. So that's part one. Due on Friday, a normal thing, upload to Blackboard, fix it up if you've got issues. If you don't, you're good. You can start working on part two, where we're going to put numbers into that total pitching moment equation that we came up with in part one, and calculate CM0 and CM alpha for this particular airplane. And where we're heading with this is that throughout all of the homework assignments, notice we've been building up an airplane. We built a wing and calculated everything we need to know about it. We added a canard, and now we've calculated everything we need to know about it. And then we're going to be able to calculate the total lift of our airplane and the total pitching moment, which means then we can trim the airplane and we can see if it's stable. We'll add a vertical tail later on and talk about lateral directional stability, that is yaw stability and bank angle stability. And then you guys will put this airplane into X-plane and fly it. So we're really virtually building, I guess it kind of fits the COVID thing, right? We're virtually building an airplane as we go throughout this class. So we've spent time talking about pitch trim and pitch stability, so we know how to design an airplane to do that. Most airplanes have elevators on them. So I want to walk our way up to that point by looking at the pitching moment equation that we have now and look at, well, what are the things that we could use to control pitch trim and understand why most airplanes have an elevator on them. So I'm going to write that formula up here. I'm not still sharing, am I? No. Is it distracting for you guys to have the video feed up there, or is that okay? It's no big deal, okay. So we're looking at longitudinal control. I guess we could insert in here pitch control, because it's the pitch of the airplane that is longitudinal. It's longitudinal motion is forward, up and down, and then pitch, because it's all in a kind of a vertical plane, right? You're going this way, and you're rotating like this. So that's longitudinal motion. And we're talking about equilibrium, which we refer to as trim, or you can think of it as kind of statics. Although the airplane's moving, we say that the velocities are all constant and the pitch angle's constant. And in fact, that's our definition, is that the net pitching moment applied, this is the total, is the sum, essentially the sum of the total moments is equal to the moment of inertia, the mass moment of inertia about the y-axis, because that's what we pitch about, times theta double dot, or pitch rate Q is theta dot. So either way you look at it, if the net moment is 0, then both the pitch rate and the angle, the pitch angle, are going to be constant, not 0. This is going to be 0, and the pitch angle is going to be constant. Sorry. Yeah, that's good. Q dot's going to be 0, so Q is either going to be 0 or constant. I'm not saying that right. Q dot is going to be 0 and Q is going to be 0 because that's theta dot. So we have 0 pitch rate and the pitch angle is constant because there's no derivative of it. So that's pitch trim, and we usually refer to it in terms of coefficient. We have no net moment, then we have no change in pitch angle. So we're at pitch equilibrium. So we're going to expand out our formula for the total pitching moment because we want to look at, well, how do we make this a 0? What can we control inside here to make it 0? So I'm going to write out our expressions that we have for CM0 and CM alpha. And this is exactly the same thing that you have on your homework for the canard airplane. This is just the total pitching moment of the airplane. So here's the whole deal. I'm going to rewrite that formula up here. CM is CM0 plus CM alpha times alpha. And so this thing, we know this. For the Cessna airplane, we calculated this and we got numbers here, right? So really, this is just the equation of a straight line. So the total pitching moment versus angle of attack isn't a straight line because it's the intercept plus the slope. And if the airplane, we're going to draw this for a stable airplane, a pitch stable airplane, then is it going to slope up or down? Yeah, because we want negative. So it's going to look like this. And this is our CM0, it's the intercept. So when alpha is 0, then that's the pitching moment, so that's the intercept. And then the point where pitching moment is 0 is our trim angle of attack. So we call it that. That's the angle of attack here that we fly at that makes this whole thing 0. Well, that's, sorry, take that, erase that from the record, the court records, I'm kidding. But, so I need to talk more about what alpha trim is. But the CM0 plus CM alpha times alpha trim has to be 0 for the trim condition. So then the thing is, well, how can we make that happen? Because this line could be up here if we shift CM0, right? If we change CM0 to a different value, call it prime, we're up there. And if we change the slope, maybe we still have the same CM0, but if we change the slope, we're going to get a different line. So how do we make sure that CM total is 0? What are the things in here that we can change? In other words, what can we change to control or make CM equals 0? So let's look at all the options in the equations. So let's start with CM0. So these are the things in CM0 that we could change. The wing is pretty much set, right? Unless we start fiddling around with the camber and actually changing the shape of the wing, that's going to be pretty much fixed. That's just a pure couple. Propulsion, we could potentially tilt the propulsion, the engine up and down. So we could tilt the engine. We'll talk more about that. Hopefully I'll remember to do that. Let's see, what else can we change? We could, the downwash is pretty much fixed by the wing. Looks like we could change IT. We could tilt the tail up and down. We could change LT bar, the distance, because that's inside here, right? So we could move the horizontal tail backwards or forward. Need to talk more about that. Lift curve slope of the tail is pretty much fixed by the geometry. So is the lift curve slope of the wing and the areas. I mean, I guess we could change the area of the wing and the tail, but that's hard to do. Unless we had like flaps maybe that slid out and made the wing bigger or the tail bigger. But practically, that doesn't help out a whole lot. So let's see, we've got these things. And then how about CM alpha? Because if we want to tilt the slope, then we can control where CM alpha is 0. So we look at this formula. Neutral point of the wing body is pretty much fixed, so is the lift curve slope. But we could certainly move the CG around. So, I mean, actively, not just load cargo and the CG shifts because of how we load it. VH bar, again, we could change LT bar so we could move the tail back. And we could also do the propulsion to trim as well. And some of these are done. A lot of fighter aircraft will have an all-moving tail where the whole horizontal tail or the canard will tilt. And that is a very effective way to achieve very powerful pitch control. Structurally, it's harder to do because then you've got to have some kind of a hinge or a pivot point that carries the whole load of the tail through that and still allows it to move to the airplane. So that is an option. Tilting the engine is an option. But then structurally, you've got to have that engine mount made so that it can tilt the engine. Right? We do that with vertical takeoff and landing and some other airplanes. Most of the reason that the engine's on the airplane is to overcome the drag, though. So if you want an efficient airplane, you don't necessarily want to waste any of your engine thrust on trimming the airplane. You want it totally there counteracting the drag. So that's not a great option. An LT bar, we could slide the tail back and forth. But then again, you've got to have the structures there to do that. You've got to have the moving joint that makes the fuselage longer or shorter. But that's effective as well. So of the things we've listed here, this one is the most commonly used rather than LT bar or the propulsion. We could move the CG. You could have a big giant block of lead inside your airplane that you slide back and forth. And that's feasible, right? But then you've got the extra weight of the lead there that's just used to control the airplane. I guess you could have all the passengers move around. That'd be kind of weird though, right? To trim the airplane. But there are airplanes where you move the CG to trim the airplane. Anybody think of one? The what? You could shift fuel, but I'm thinking of an even simpler airplane. Anybody know of one where the pilot moves himself back and forth to control the airplane? You know what? Yeah, so you're thinking of a hang glider. So the pilot hangs below the wing, and they actually have a bar, and they push themselves back and forth, and they use their CG to control it, because in that case, it's easier than having a joystick and a cable and an elevator and everything else, because it's a real simple airplane. So a hang glider here. See if anybody in the chat said anything. Could you have variable sweep? Yeah, you could. You could sweep the wings forward and back. Typically, that's done to allow you to fly at high Mach numbers or slow Mach numbers, but you could sweep the airplane as well. And we don't really have that in here. If you change the sweep angle, then that changes essentially this, the pitching moment, because you're sweeping the tips back, and that changes the pier couple of the wing. So we've said, okay, well, if we have a certain curve here and we have an alpha trim we want to trim at, then we need to make sure our curve goes through that at 0, so that we get pitching moment of 0 at alpha trim. But what alpha do we fly at? Because here we're saying, okay, well, at the right alpha, we need to make CM 0. So that's, I just want to remind us real quick of what the answer to that question is. So here we're talking about we're going to fly at an alpha, and then how do we make CM 0? But more fundamentally, what alpha trim do we fly at? And do you remember from 324, what's the criteria for calculating alpha? What alpha do you fly at? Why do we have an angle of attack to begin with? Why do we care? Alpha angle of attack produces lift. Why do we need lift? Yeah, so we got to counteract the weight. So that gives us the angle of attack, is that for level flight, lift equals weight. So then CL trim, we're talking trim now. The CL trim is the weight divided by 1/2 rho V infinity squared S. And so the weight goes in here, and CL is the lift curve slope of the airplane times alpha. And so that's where we get the trim. for level flight, we have to have enough alpha times the lift curve slope to balance out the weight of the airplane. How about if we're doing like a 2G pull-up? By the definition of G's, that means we have twice as much lift as the weight. So that means we have to have 2, and that changes alpha trim. And so then we know what alpha trim is, and that goes in here. I lost my formula, right? CM alpha multiplies alpha, so that goes in there. And then we have to calculate, well, what IT, I'm pointing to this and they can't see it. We have to know what IT we're going to fly at. So the alpha trim comes from here, and then if we're trimming with IT, comes from making CM 0. All right, so that's the whole trim story. This is effective, alpha IT trim is effective, but a simpler method, both structurally and mechanically, and just getting enough power but kind of not overdoing it, is to add an elevator to the horizontal tail or the canard. And what that does is it changes the camber. So it changes the lift of the tail, because we know if we have a flap on the end of an airfoil, you tilt it down, it shifts the lift curve slope up, you tilt it up, it shifts it down, so it changes the camber and it changes the lift of the tail. And then of course the lift of the tail feeds in to the total pitching moment. So you don't have to build an airplane with an elevator. You can do an all-moving tail. You can shift the CG back and forth, but this is a very effective and fairly simple method to control the pitch of the airplane. It's essentially a flap on the trailing edge of the tail. So we need to define the elevator and the terms that we need to go into the formula. So let me know when you guys are done over here on the right, because I'm going to shift over to the other board. So the elevator, and this is the angle, is called delta E. And if we draw the tail, which is really just a wing that we put in the back, the elevator is a flap on the end of it, and draw it downward like that. The normal chord of this thing would be like through here. And this is the angle delta E. And that's positive downward. So positive elevator angle is trailing edge down. And so you look at that and you go, you're increasing the camber, so the lift is going to increase. So if we plotted the lift of the tail, let's say it's a symmetrical airfoil, so it goes through like that. This is for 0 elevator. If we deflect the elevator, the lift goes up like this. Let's say we went up 10 degrees like that. And let's say it goes up to 0.2. So that means that the change in lift of the tail with respect to elevator deflection is going to be 0.2, right? It's sorry, 0.02. It's going to be 0.2 divided by 10 degrees, so it's going to be 0.02 per degree. And you could test this in the wind tunnel. You take your horizontal tail, you put it in there, and you deflect the elevator through 5 and 10 and 15 and 20 degrees, and then you do a plot of the lift curve of the tail. But we're more interested in the tail added to the airplane. So what we really care about is, this is versus alpha tail, is the total lift of the airplane versus elevator. But we're going to get the same effect. It's just going to be reduced because the total lift of the airplane includes the wing. So we can take the entire airplane and go in the wind tunnel and measure the lift versus alpha for different elevator deflections. And we could also measure the total pitching moment of the airplane for different elevator deflections. And what we would get is information on how the elevator affects the lift and the pitching moment. And so we'll say, well, we're just going to add on the extra lift of the elevator and the extra pitching moment of the elevator. So we'll call it delta. That's extra lift due to the elevator for the whole airplane and extra pitching moment of the airplane. And we're going to write this. So this is really a definition. We're going to say CL delta E times delta E gives us that extra part. And if you look at this, this is really a derivative, how the lift changes with elevator deflection. And the same thing here. So we're defining just like we calculate, say, the lift of the tail as its lift curve slope times its angle of attack. Here we've got a slope, but it's not the lift curve slope, it's the elevator lift curve slope. So we take this slope times the elevator. So CL delta E is the derivative, not with respect to alpha, but with respect to elevator. Like that. And CM, that's just the change in pitching moment, the delta pitching moment per degree of elevator, and then we multiply by how many degrees of elevator we have, and that's how much delta CM we get. So typically we calculate like the lift of the airplane is the lift of the wing plus the lift of the tail, and we'll normally know from charts in the back of the book how a flap on a wing changes its lift. And so we'll be able to predict this from the charts, just like that's how we got the lift to add into the total pitching or the total lift of the airplane. So we'll go back there and we'll get everything in terms of the tail itself, all by itself. And so we need formulas on how to add in the tail into the total lift and the total pitching moment to get these numbers that'll go into our formula. And then what we end up with are our normal equations for lift and pitching moment. So our equation for lift is the total lift curve slope of the airplane times alpha. And there's a lot of work that goes into calculating that. You guys have seen that, because that is adding the lift of the wing plus the lift of the tail and then moving stuff around to make it look like that. And so now we're going to add in an elevator, and we do that by adding that extra delta CL. So that's our new formula for the lift. If we have no elevator, elevator is 0, that goes away and we're back to what we had before. So this is the extra part due to the elevator, and part of the elevator rubbed off on my paper. And the same thing for the pitching moment. There's the pure couple stuff. Here's the pitching moment we get from angle of attack. And then we add on the extra pitching moment we get when we deflect the elevator. So if we have an elevator, now these are our new equations. And if we wanted to trim the airplane, we would say, well, our total lift has to be the weight divided by 1/2 rho v squared s. And then we'd have to calculate the angle of attack and the elevator that give us that lift. And notice now, these two equations have to be solved simultaneously because it's two equations and two unknowns. Whereas what we did before, there was no IT in our lift equation. Over here, when we were trimming the airplane where we were using IT, we can immediately solve for alpha here and then go to the pitch equation and solve for IT separately because we already know alpha. But with the elevator changes the lift and the pitching moment. So you'll see that we'll do in our homework, I'll ask you to trim the airplane two different ways using IT and elevator. And don't be confused if it's really easy to calculate the IT and the alpha for that problem because they're coupled, they're not decoupled, whereas here we have to solve two equations and two unknowns. All right, so how do we get these numbers that go in here? From our airplane design, we designed the horizontal tail, we designed a wing. Now we've added an elevator, which is really just a flap. So I'm going to give you the formulas for that, and then we'll be good to go. We can add an elevator to our airplane. Okay, way back when we added the two different lifts together, we added the wing lift together with the tail lift, and that was the formula we got. So where does the elevator affect this? The elevator changes that. It doesn't change the lift of the wing because the wing is way up front. So if we're looking at the derivative of this with respect to elevator, this is 0 because it doesn't affect it. We get ST over S, and then we get that derivative that relates to that lift curve slope I was showing you for CLT. And this is how does that flap on the back of that wing built with an airfoil that's the tail affect the lift of the tail. And to do that, you need the results of airfoil or wind tunnel tests on wings where there's a flap. We don't care what the flap is. We just want some wind tunnel data for the flap. We call it an elevator, but it's really a flap. And this comes from Appendix B.2, page 321, and page 35, equation 2.4, 8. And we don't have, other than taking wind tunnel data that's condensed into those tables, we don't have a good way to predict the lift of the elevator that it generates any more than we know how much lift versus angle of attack comes from an airfoil, right? To get the airfoil lift, we have to go to the airfoil tables in the book and calculate the lift curve slope and all of that stuff. So fundamentally, it all goes back to when they tested these kind of wings and airfoils and the effects that they have on them. And then how do you get the pitching moment of the elevator? This is the A sub E thing that we get from the appendix. And then there's the effect of the elevator on the lift times the moment arm. Oh, and that's this equation here that's on page 35. So for the homework in the future, and if you're designing an airplane, go to the appendix to get this number here. Then you use this formula to calculate it. And then you got that number from the appendix. And we know CL delta E, that's the number we just got from up here. So that number that we calculated goes in here. This comes from the appendix. You multiply and you got the pitching moment effect. And this formula really just comes from taking the derivative of that big pitching moment formula with respect to elevator, right? That big long thing that I wrote first off when we started talking about trim, the lift of the tail and the total lift of the airplane both depend upon elevator. And so that's where those two terms come from. So you probably realized by now, but throughout all of your science and engineering classes, is that you can derive formulas and come up with formulas and model what you're doing with Newton's law or whatever. This is aerodynamics, right? But at the bottom of everything, there's always experimental observations that we create math models of that allow us to do calculations. Like, how is the lift of an airfoil vary versus angle of attack? Experimental observations on airfoil data. And that's true of all the science, whether it's exploring Mars, where we've done observations of how the planets move and develop Newton's laws and all that. We're doing quantum mechanics, where they study how blasting particles into atoms and seeing these pieces and parts come off. And they observe what happens and measure things, and then they develop mathematical models that aren't reality, they're just models of what can be observed. So the nice thing about us engineers is we use the data that other people. Right, that's the end of today. Next time we will talk about, I knew what it was a minute ago. Oh, we're going to trim with the elevator now. So we're going to take these two equations and talk about solving them simultaneously for trim. All right, quiz on Friday, homework due on Friday. Next homework's due next Friday, not at the end of March. I'll fix that up. Let's see, somebody has a question on here. Do we have equations provided for question 2? Part B and G, what's that? I think we went through that, didn't we? What is it, part B? The canard lift curve slope is the big giant formula for the lift curve slope. And what was the other one, G? Yeah, there's formulas in the lecture or in the class notes for what VC and VC bar are.